Hello everyone, this is Rajan Ramachan. Let me give you a brief introduction about the central limit theorem and I'll show you a Java template how this central limit theorem works. Central limit theorem is about the distribution of the sample mean.
Many people confuse with the concept of central limit theorem. Central limit theorem is not about the distribution of the data itself, but it is the distribution of the sample mean.
For large sample size n, the distribution of sample mean when you draw several samples and plot them, then the distribution of the sample mean will be the normal with mean equal to the population mean mu and the standard deviation is equal to the sigma over square root of n, where sigma is the population standard deviation. What it shows is if you don't know the population mean mu also, then you can use the concept of sampling distribution to estimate that value of mu. Similarly, you can also use the same concept to estimate the value of the unknown population standard deviation sigma. So mean of the sample mean is equal to mu or the population mean and variance of sample mean is equal to sigma square over n, where sigma square is the population variance. What central limit theorem says, you are drawing several samples of same size and usually we consider size more than 30 is good enough, and in statistics size more than 30 is considered large. Calculate the mean for each of these samples. There are n samples, assume that, and we calculate the mean for each of these samples, and then if you plot the histogram of all those means, not x but x bars, okay? So if you plot the histogram of all sample means, then the histogram looks like normal. And this is what the central limit theorem is. No matter what population, what the parent population is, whether it is normal or non-normal, any kind of distribution, it doesn't matter. If you draw the sample and make diagram of all these sample means, then it will always be normal. That's what the central limit theorem. As I said, the mean of the sampling distribution of sample mean is approximately equal to the population mean and variance is equal to the population variance divided by sample size. Let me show that from the simulation here. Now let's start with a simple example, and for convenience for this example, assume that we know about the population mean and population variance also. In general, population characteristics, which are called the parameters, they are usually unknown. That's one of the reasons why we need to use the sample information to estimate them. If you already know everything from the population, then you don't need to use any sample. Now, assume that this is a parent population, this is the actual population, and we don't know the size of this population, but assume this is a large population with the mean 16 and standard deviation 5. Now, this is a normal population and we want to draw a sample from this. So let me just write down this standard deviation information in my Excel sheet. This population standard deviation I have 5. Now, I want to draw a sample of size 25 from this population. Okay, let me draw one sample of size 25. So there are 25 different objects from this population is coming to the sample. Now, there are 25 different items coming from this population. And what I do is I don't record all of these observations, whatever came to the sample, but I want to record average or the mean of that 25 observations. So this is the mean from the first sample. And now this is the mean from the first sample. Now what I want to do is I want to repeatedly take several samples of same size 25 and just collect this mean. My interest is this mean, sample means, not these sample data. So let me collect this. Let me do another sample of same size 25. So this sample could have any random elements. So the another mean came out very close to this one. Similarly, you can repeat this process several times. When you repeat all these process and just collect the sample means here, what could be your best guess that how this sample distribution looks like? Does it look like same parent population like normal, or it looks like a different distribution. Your best guess is okay, it looks like a parent population, normal population, yes, because it is coming from this population, so it may look like that. So let's repeat that for 5 times. Then there are 5 means here. Now let's repeat this 10,000 times. When we repeat 10,000 times, the distribution of sample mean looks like this. Now if you repeat that 100,000 times, then it looks very similar and a little bit narrower. And now when we repeated this several times, this is also a normal distribution, just like this one, but it has very narrow spread, means its variance is narrowed down. So let's calculate this variance, whatever the variance here. Now the standard deviation turned out to be 1. And notice that the population mean, the exact population has a mean 16. Now when we draw only the samples, the mean of the sample is also 16. It's exactly the same. Means even you don't need to know this population mean. If you know the distribution of sample means, you know the exact value of the population mean also. That's one of the advantages. And now let's compare the standard deviation. There is 1 here. Now let's go back to my Excel sheet here. I took the sample of size 25. This is my sample of size 25. Now when I repeat this several times, now my expected standard deviation based on the central limit theorem will be sigma over square root of n. So sigma is 5. Let me just write down this 5. Sigma is this 5 divided by square root of this 25. This gives me 1. So my expected standard deviation based on central limit theorem should be 1. Now let's see what is the actual value of sample standard deviation from the simulation example. Now if you go and see the simulation example, this is exactly 1. That is a very good example. Now let me go to another example. You may think that we get this population distribution normal because our parent population was normal. Now let's change this population, because
In reality,
we can encounter any kind of data. So let's say my data looks like this. It's kind of weird data. There is no shape of the data. When you draw the histogram of the data, it looks like this. Now let me do the same thing. For this data, mean is 1518. Let me note this down here. This mean is 1518. Let me write down these mean values here. Mean from the population is 15. And standard deviation of this population is 9.31. And I'm planning to take the same sample size of 25. If I take this one, then my expected standard deviation based on the central limit theorem should be equal to 1.862. Now let's see whether I get 1.862 or not. And I also want to see whether I can come close to this population mean just by using the sampling distribution or not. Now let me go back here. So this is our population which has the weird shape. Now let me take the sample of size 25. Just take one sample first. Since this data is very spread data, it has larger variance. We have one sample mean here, so I'm collecting one sample mean. Now let me do another animation also. So the another sample mean is here, means this is a data with a larger variance. That's why your sample means could be anywhere. Now if I repeat this process for a long period, if I repeat the same sampling process and repeat this for 10,000 times, then how the shape of this sample means looks like. You may think it looks like something like this, but no. It doesn't matter how this parent population is. If you repeat this, then this looks like normal. You see, if you repeat this 10,000 times, then the distribution of the sampling mean is normal. Now let's see its properties. I repeated 10,000 times and let's calculate the means here. The mean of all these sample mean is 15, 15, and standard deviation is 1.86. So let me just write down here. This is the actual standard deviation from the simulation, and this is 15.15. Now look here, how close these are, and notice that these two are usually unknown. Okay, these two are usually unknown values. So these two are unknown values, and now even this is unknown. Now we can easily calculate them. This population mean is unknown, but using the sampling distribution, we can so close to the actual value. And this is the standard deviation of the sample mean, and from this it is easy to obtain this. Okay, because the expected value 1.86 and 862, but we get 1.86. That's very close. So the central limit theorem, whatever we define based on central limit theorem, is exactly what we can see from the simulations. Now let me go to one extreme example. Now sometimes you may see that okay, our data is kind of uniform, flat data, almost same thing. And even for this kind of worst data, here this data has mean 1528 and standard deviation 922. Let me just write down there. Mean is 15.8 and standard deviation is 9.22. Now I'm using the same sample size, or maybe I can change the sample size a little bit here. This time I want to show you a little bit different thing. Let's say this is 16 now instead of 20. Now we have sample size is 16. Okay, let's 16 sample size here. If our central limit theorem is correct, then the standard deviation of the sample mean should be 2.305, and the mean should be equal to 15.28. So let's see that on through the animation here. Now let me get one sample of size 16 and take the mean, collect the mean, what is there. It's very straight data, so you can find mean anywhere. And you can repeat 5 of them, then these are the 5 means. Now repeat 10,000 times, still you get the same normal distribution for the sample mean. So no matter what the parent population is, your sample mean always follows the normal distribution. And if you go see closely here, then the mean is 1531 and standard deviation 2.31. Let's see, mean is 1531 and standard deviation is 2.31. So these values matches here. So this is the central limit theorem. You don't need to know the actual population mean or population standard deviation if you know the distribution of the sample mean. And mean of the sample mean is equal to the population mean, and standard deviation of the sample mean is equal to the sigma over square root of sample size n.